Okay, good afternoon or evening. This is an example from chapter 16-2 homework assignment. It's the example we did in class. Each problem is asking you to do a lot of things. We've got some data here, and instead of the directions telling you, okay, this is linear, this is exponential, this is quadratic, we're getting the data and we're not being told what it is. We're going to have to use either the graph or some information from the calculator to figure it out. Before we even start the problem, let's set up the calculator. So we're going to hit second plus 712, just kind of clear everything out. You don't have to do that in between questions, but just to start with, it would be a good idea. And a couple things you're going to want to turn on. First of all, you're going to want to turn on Diagnostics. So that is second, catalog, alpha, D, get down to the D's, or you could just scroll, but it's easier to go alpha, D. And too far. Turn Diagnostics on, enter. But remember, you have to hit enter again till it says done. Okay, the second thing I want you to do is go second stat plot and turn the stat plots on. Right now they're off by default, so I hit enter. And then the off is lit up. I want to hit enter so that on is lit up. The type of graph is by default the scatter plot. That's what we want. Okay, so our calculator is set up. Let's go back to the problem. This says the table shows the population of river otters in a river over a period of time. Well, I see that as time goes by, the data is increasing. And I see it's increasing by 2, and then by 4, and then by 5, and then by 9, and then by 14. So it's probably not linear. But we're going to graph it to see what it looks like. So this is the time is the x-axis. 0, 1, 2, 3, 4, 5. And on the y-axis, we need to go at least as high as 40. If you count by 5s, you make it. Okay? Then we're going to make here's our first step, we're going to make a scatter plot. Okay? Do not connect the dots. Scatter plots mean that you do not connect the dots. Okay? And so 0, 6, 1, 8, 2, 12, 3, 17, 4, 26, 5, 40. Okay, so what I'm seeing here is a slight curve. Okay, so it's telling me it's not linear. Okay, so the next thing I'm going to do is I'm going to enter my data into L1 and L2. Okay, stat, edit, 0, 1, 2, 3, 4, and 5. Okay, 6, 8, 12, 17, 26, and 40. Oh no, I was hitting plus all that time. Okay, now it's in there correctly into L2. So we're pretty sure there's a curve here, so it's not linear. However, it's really hard to tell if this data is quadratic or exponential because it's a curve, and they're both curves. One way that, although this picture doesn't show it, if I could see dots where they went down and then back up again, then I could say, oh, that's quadratic. But these dots just kind of curve down, and I can't tell if it would curve up on the other side or if it would just continue to go down. So because I can't tell, anytime you have a curve, when you're trying to decide on the regression, whether it's linear or exponential, curves could be either one. So you're going to do both regressions and look for the higher r squared value. Okay, well, Mrs. Andrews, why r squared? Well, you'll see in just a minute. So if we do stat, calc, let's look at the quadratic regression. Okay. Okay, usually we look at r, but unfortunately, this only gives us an r squared. Okay, I'm not sure why that is, but it only gives us an r squared. I'm going to pull that out and put that up there for a second. Okay, let's do the the exponential regression. Remember, that's option 0. You can just push 0, or you can scroll down to it. Enter. Okay, I'm going to pull that out so we can look at both of these side by side. Okay, so all of that this gives me is an r squared. Okay, and it's capital R, and this is lowercase r, but that's okay. They mean the same thing. Okay, so when you have a curve, you have to do both the quadratic and the exponential regression. And what you're looking for is, remember, the best fit is the closer value to 1. So this is 0.995. This is 0.996. So the exponential regression in this case is going to be the better choice because the r squared value is higher. Okay. Oh, I moved that. All right, so this data is exponential. And our regression equation is f of x equals 5.665 times 1.465 to the x power. The directions don't specifically say what to round to. And the example from question 1 does hundredths. I did thousandths. Hundredths or thousandths is fine. I'm not really worked up about which place value it is. As long hundreds or thousandths is fine. Okay, so there's the regression equation. Okay, now here's where it gets confusing, because remember where I said don't connect the dots? Okay, the next part I'm going to do is going to look like I'm connecting the dots. All right, so going into our calculator here, the reason I had you turn on the stat plot is because I want you to hit zoom 9. And you get a nice pretty picture that somewhat matches the graph that you drew. Okay, what we're going to do now is take the regression equation that we got and put it in the y equals. Okay, and just watch what the picture does, because what the picture on the graph is going to do is exactly what I want you to do. And in fact, I'm going to change the color over here so that the color doesn't make things look too similar. Let's actually make the color red. Okay, so now I'm going to hit OK. And I know that your calculator may not have the ability to do color, but this is just for you to see on the screen. Okay, and graph. So we've got our dots. Aha. So the red is the line or the function line of best fit. I am not connecting the dots of the original data. It looks like it because the function models the data really well. In other words, the function follows pretty much the same path as the dots. That means our data is really close to this model. But you can see sometimes the line is at the lower end of the square. Sometimes the square is barely touching the line, like these two spots. Here it passes right through the square. So there's slight variation. So what we're going to do is go into the table and graph these points. These points represent the function, not the data. Okay? Take this out. Look at it. Now, I would recommend that you change color and maybe even consider you could draw an X instead of a dot. Okay? So let me move these things out of the way. Don't need those anymore. Okay, so I would recommend maybe an X or a different color dot, or both. 0 and 5.665. That's super close to 6. It is just under it. In fact, I'm going to make the X pretty much touching the dot slightly underneath it. Okay, 1 and 8.292. Okay, that's a little bit above. So I'm making it, it's still touching the red dot. It's so close. 2 and 12.158. Okay, super close, just slightly above. 3 and 17.8. Well, okay, so that's 17.812 is pretty close to 18. So that's maybe a little bit more above the dot, maybe not quite so touching it. Okay? 4 and 26.095, that is super close. Practically touching it. And 5, 38.229. Okay, this was 40, so it's actually 2 below that, so not so close. All right, so these points represent the function I would use if I wanted to know what the population of river otters is going to be in 10 years. I don't have data that goes out 10 years. So the purpose of drawing this second part, the blue X's and the line, the nice curve I'm going to draw with the blue X's, if I continued this graph out to 10, that's what I would be using in order to predict out to 10 years, would be the line from the graph or the table. I could go and say, oh, I think there's going to be about 258 otters if I look at this chart here. Okay, so that's how you're doing your homework assignment. Number 3, the scatter plot of it, I will say in number 3, does seem borderline whether it's going to be quadratic or linear. However, if you do a quadratic regression on number 3, it gives an A value of 0, and you cannot have an A value of 0 with a quadratic. So number 3 is linear, but that's a common question that I got in class. All right, I hope this was helpful. Have a good night, and I'll see you tomorrow.